The cosmos is an endless expanse where stars and planets have been forming and disappearing for billions of years. Imagine how in this infinite vacuum, amidst the radiance of billions of stars, celestial bodies are born. We usually think of Earth as something constant and unchanging, but in reality, our planet is the result of a complex process that began with clouds of gas and dust rotating around a young sun. This cloud, known as the solar nebula, consisted of hydrogen, helium, and heavy elements formed in the interiors of previous stars. Over millions of years, particles in this cloud began to collide with each other, forming more massive clumps of matter. Each collision was like a small, explosive reaction that ultimately led to the formation of planets. We can only imagine how this process unfolded over billions of years, where time stretches to unimaginable scales. Thus, Earth began to form around 4.5 billion years ago, but this is just a blink in the context of the entire history of the universe, which spans over 13 billion years. During this formation, the planet was subjected to attacks by meteoroids, comets, and asteroids, each leaving its mark on its surface. These collisions could have seemed catastrophic, but they were also necessary for the formation of the atmosphere and oceans, which later became the basis for life. Compare this to the work of a sculptor, who gradually shapes a stone block using a hammer and chisel. Each blow is a step towards creating something great and significant. So, Earth, passing through thousands of years of chaos and destruction, gradually acquired its form and identity. We embark on this extraordinary journey through time to understand how a celestial chaos gave birth to the planet we live on. This journey requires not only courage, but also the willingness to grasp the scales of time that are difficult for the human mind to comprehend, where millions of years are just units of measurement, and each period is an entire epoch in the history of Earth. Each layer of rock, each mineral in the ground, these are not just stones. They are records of history waiting to be deciphered by scientists. Every discovery made by geologists and archaeologists opens new pages in this endless book of time, where each fact is a piece of a puzzle that helps restore the amazing and complex picture of our past. For example, studying fossil remains, scientists can understand how the climate changed, how life evolved, and how various factors influenced the ecosystem. It is interesting that the study of ancient layers allows us not only to look into the past, but also to draw conclusions about the future of our planet. And each such discovery is not just numbers and facts. It is a living testimony of how complex and diverse the path of Earth was to become a home for billions of forms of life. The formation of the protoplanetary disk around the young sun is a magnificent and complex process that began approximately 4.5 billion years ago. At that time, a gigantic cloud of cosmic dust and gas, primarily composed of hydrogen and helium, began to slowly rotate under the influence of gravitational forces. This cloud, known as the solar nebula, gradually condensed, creating swirling motions in which particles collided and coalesced, forming larger aggregates. Meanwhile, the temperature in the center of the cloud rose to thousands of degrees Celsius, resulting in luminosity that created a bright light source in the surrounding cosmic darkness. This process, known as accretion, took place over millions of years, and with each rotation of the disk, it became brighter and denser. The outer regions of the nebula remained cold, creating a contrast between the bright light of the central area and the dark, nearly infinite expanses around it. Temperatures in these distant areas could drop to -200 degrees Celsius, facilitating the formation of ice and other volatile substances. Meanwhile, particles orbiting the young sun began to form planetesimals, protoplanets that would not only contribute to the formation of planets, but also reshape the entire solar system. This cosmic dance of matter occurred slowly but inexorably, providing a unique opportunity to study the processes that ultimately led to the formation of Earth and other planets. In this disk, spanning tens of millions of kilometers, a true symphony of low-frequency sounds was played, caused by particle collisions and gas oscillations, creating an atmosphere of cosmic grandeur and mystery. Complex interactions between particles led to the formation of dense clouds that then began to condense into larger structures such as comets and asteroids. These primary forms of matter retain traces of the ancient solar nebula, and their study can provide us with keys to understanding the early history of the solar system. Ultimately, it was this protoplanetary disk that served as the foundation for the formation of Earth, which, in turn, became a home for billions of forms of life. The process of accretion is a remarkable phenomenon in which the smallest cosmic particles gradually coalesce into larger bodies. In the early stages of the solar system, tiny dust particles, composed of minerals and ice, collided with each other in near-vacuum conditions. These collisions, occurring at speeds of just a few centimeters per second, were so slow that they could be likened to a hypnotic dance of matter in the silent cosmos. Research indicates that the process of accretion takes millions of years to form significant objects such as asteroids and planets. Scientists like Dr. Alan Boss of the Carnegie Institute emphasize that during this time, collisions occurred over epochs, creating conditions for the formation of larger pebbles, which then combined to form protoplanets. As particles collided, they adhered to each other due to electrical and magnetic forces, forming what are known as aggregates. These aggregates, composed of numerous small particles, grew larger over time, reaching sizes of several centimeters. Thus, they formed more substantial bodies that eventually became the precursors of planets. Imagine small pebbles slowly orbiting each other in the silent cosmos, with low gravity, colliding, adhering, and forming new shapes, a process that developed slowly but steadily. Such collisions could resemble a choreography, where each movement repeats and changes over millions of years. These movements not only form comets and asteroids, but also create conditions for the formation of moons, when larger bodies collide and eject material into space, which then begins to rotate and form satellites. Events such as the collision between Earth and a hypothetical planet Theia, which occurred around 4.5 billion years ago, are also part of the long process of accretion that formed not only planets, but also their moons. Scientific research shows that accretion is not just a physical process. It is a complex system of interactions between material particles that ultimately leads to the creation of stable objects in the solar system. Each step of this process, each small detail, is significant, as they form the foundation for the formation of the universe as we know it today. At this stage of solar system formation, within the protoplanetary disk, planetesimals emerge, large bodies ranging from several hundred meters to several kilometers in size. Gravity begins to play a crucial role, attracting more and more matter to the already formed centers, creating a snowball effect. The more massive the object, the stronger its gravitational pull. This leads to thousands of rocky bodies of various sizes orbiting around the planetesimals, quickly moving along their orbits, colliding and merging with smaller fragments. At this time, the cosmic space resembles a giant battlefield filled with debris, where each collision can result in the formation of new, larger objects. Around 4,700,000,000 years ago, these interactions were constant in the disk, leading to the formation of bodies that would eventually become planets. For instance, scientists like Dr. Alan Boss from the Carnegie Institute note that these initial collisions and gravitational interactions were instrumental in the formation of planets like Earth and Mars. These early planetesimals, with their robust structure and sufficient mass, began to absorb surrounding material, creating a contrast between their solidity and the emptiness of space. They were not just rocks, but the fundamental building blocks for the formation of planets that would later acquire atmospheres and even life. Their motion and interaction in the cosmic vacuum paint a dynamic picture. Each object, orbiting its path, contributes to the process of planetary system formation. As a result of these interactions, more complex structures, such as binary systems or even protoplanetary disks, can form, which may eventually give rise to new stars. Just as a sculptor works with stone, gravity shapes these cosmic bodies, giving them various forms and sizes. Scientific data from missions like Diane and Cassini have confirmed that these processes were critically important for the formation of planetary systems in our universe and beyond. The process of forming proto-Earth can be imagined as a majestic and slow awakening, in which numerous planetesimals, small bodies formed from gas and dust in the protoplanetary disk, began to coalesce into larger structures. These planetesimals, ranging in size from small pebbles to objects the size of mountains, collided with each other, creating side effects that can be compared to a dance in the vast expanse of space. Each impact, each collision scenario triggered a chain reaction where particles gathered, merged, and formed larger aggregates. This process, which took millions of years, resembled the slow crystallization of a solution. Initially, everything seemed chaotic, but over time, clear and stable forms emerged. Scientists like Dr. Edward Chi of the University of California have shown in their research that ultimately, due to gravitational attraction, these objects began to form a protoplanet, which eventually became the foundation of our Earth. In the early stages of proto-Earth formation, collisions were so frequent that the new body, composed of a mixture of rocks and metals, was subjected to constant impacts, which led to the release of enormous amounts of heat. This heat facilitated the melting of internal layers, which in turn created conditions for differentiation, where heavier elements such as iron sank to the core and lighter elements rose to the surface, forming mantles and crust. Thus, gradually, over millions of years, structures were formed that we now observe on Earth. Scientific models show that at this time, volcanic eruptions could have occurred on the surface, ejecting gas and dust into the atmosphere, creating conditions for further formation and change. These volcanic activities, in addition to everything else, could have contributed to the formation of the first oceans when condensed vapor, resulting from heating, fell back onto the surface. Thus, the process of forming proto-Earth was not only physical, but also chemical, with numerous reactions occurring in conditions close to chaos, gradually leading to a stable body. Scientists continue to study this process to understand how exactly planets formed in our solar system and beyond, paying attention to the fact that studying such ancient processes can provide a key to understanding not only our planet, but the entire universe. As a result, when Proto-Earth reached its full size, it became a dynamic body with a complex internal structure, ready for further development and changes, which in turn foreshadowed the emergence of life. In the vast expanse of space, where time and space behave differently, two planetary masses, the young Earth and the protoplanet Theia, slowly approach each other. Around 4.5 billion years ago, while Earth was beginning to take its shape, Theia, roughly the size of Mars, orbited on its path, unaware of its fate. These two bodies, each with its own history and share of energy, were hurtling towards each other, and their collision was inevitable. The process of approaching took thousands of years, and when they finally collided, this event transformed not only them, but the entire solar system. In that moment, something truly magnificent occurred, a collision that could be likened to a cosmic ballet of destruction and creation. Massive amounts of matter met with colossal force, releasing energy equivalent to millions of megatons of TNT. In that instant, molten rocks and minerals, under the influence of incredible pressure and temperature, scattered in all directions, forming clouds of molten material that rushed into space. This ejection of material resembled a fireworks display, but instead of light and sound, it was streams of magma and dust that formed temporary rings around Earth. Estimates suggest that around 30% of the mass of one of the planets was ejected into space as a result of the collision, which served as a catalyst for the formation of the Moon. During this cosmic dance, waves of molten material swept through space, creating new structures and forms. The formation of the Moon from the remnants of the collision was not merely a random event, but a crucial stage in the development of Earth and its satellite. These molten masses eventually cooled and began to coalesce, forming the celestial body that now orbits our planet. The Moon, in turn, had a profound influence on Earth, stabilizing its axis of rotation and creating conditions necessary for the emergence of life. Research indicates that without this catastrophic collision, life on Earth might have developed in a completely different way. From the debris ejected as a result of the collision with the planet Theia, the process of forming the Moon began. Around the young Earth, a disk of hot gases and particles formed, which included both small fragments and large chunks of Theia's crust and mantle. This process started approximately 4.5 billion years ago and continued for millions of years until the particles began to coalesce into larger bodies. Initially, these were small clumps that gradually merged under the influence of gravity and rotation, starting to form larger objects. This was a smooth and majestic sight. In the cosmic space filled with clouds of dust and gas, tiny fragments slowly but surely moved towards each other, combining into a single whole. Over the next 100 million years, these mergers gave rise to protolunars, which continued to grow by absorbing the remaining debris. It is worth noting that the process of lunar formation was not chaotic. It resembled a dance of cosmic particles, where each found its place in the orbital rhythm. This was the time when, in the emptiness of space, a satellite was born, which would later become an integral part of life on Earth. As the Moon grew, it began to influence the young Earth, altering its rotation and creating conditions for tides and ebbs, which, in turn, contributed to the formation of oceans. This majestic process of satellite formation took several 100 million years to complete, when the young Moon reached a stable state and took its place in the eternal sky, becoming a witness to the birth of life on our planet. As a result, the Moon, with a diameter of 3,400 kilometers, became not just a cosmic body, but also a significant factor influencing the climatic and geological processes on Earth. Due to the gravitational influence of the Moon, which over time stabilized the tilt of the Earth's axis, the early Earth was a completely different reality. After its formation, Earth was unrecognizable. It was a molten sphere of magma, where temperatures reached cosmic proportions, and its surface glowed with bright orange and red hues. There was nothing that could remind us of familiar landscapes. No mountains, no oceans, no forests. Instead, an endless ocean of fire stretched out before our eyes, where waves of molten rock churned and erupted, giving the impression that the planet was alive. Massive flows of magma rushed to the surface, causing explosions and eruptions, while the planet was surrounded by clouds of steam and gases formed by the constant thermal impact. This molten sphere was not only dangerous, but also mesmerizing. The glow reflected in the clouds gave the atmosphere a mysterious appearance. There were no signs of life, no solid crust on which we stand today. Instead, the entire planet was covered with a layer of molten material that continued to change under the influence of internal processes. Speaking of time, it took several million years before cooling began and the formation of a solid crust, marking the first step towards creating conditions for life. This was an era when the planet was on the brink of becoming, with each element of the landscape we know today waiting in the depths of this fiery sphere. At this stage of Earth's development, changes took place that would later determine the composition of the atmosphere and, ultimately, the conditions suitable for life. All this dynamics created a background context for future geological processes that would eventually lead to the formation of continents and oceans. On early Earth, about 4 billion years ago, the planet's surface was a magma ocean, a churning, glowing mass of molten rock. Imagine vast waves of magma rising and falling, creating the impression of eternal motion. The colors of this ocean ranged from bright yellow to deep red, depending on the temperature and composition of the molten material. In some places, powerful eruptions from the Earth's depths spewed even hotter material, forming craters and volcanic cones. These eruptions were so forceful that they could launch rocks kilometers into the air. Processes like convection in the magma ocean led to the formation of whirlpools of molten rock that spun at incredible speeds, creating a dynamic atmosphere around them. Surface temperatures could reach thousands of degrees Celsius, making it impossible for any primitive forms of life to exist. Water, as we know it today, had not yet formed in liquid form. Instead, water vapor rose into the atmosphere, forming clouds that would eventually condense into oceans. These conditions laid the foundation for the subsequent formation of continents, but at that time, the planet's surface bore no resemblance to the familiar world we know. The magma's composition, rich in silicates, iron, and other elements, created incredibly diverse conditions for mineral formation. Various rocks, such as basalt and granite, began to form in response to temperature and pressure changes. Energy released from the molten masses could have contributed to the formation of the first continents, though they were still in the process of forming. All this occurred amidst constant tectonic processes that, in turn, influenced the climate and atmosphere. Early Earth's atmosphere was filled with carbon dioxide and water vapor, creating a greenhouse effect, but the surface temperature was so high that no organic substances could survive in such conditions. This magma epoch was one of the most chaotic periods in our planet's history, and it was here that the foundations for subsequent life formation were laid. Gradually, as the surface cooled, the magma ocean began to transform into the primary oceans, but that is another story. The process of differentiation of the Earth's material, which occurred at the early stages of the formation of our planet, is indeed an epic process that took millions of years. While the Earth was in a state of melt, heavy elements such as iron and nickel began to gradually sink towards the center of the planet, forming the core. This process can be visualized as a slow but inexorable movement of matter within the molten mass. On the other hand, lighter elements such as silicon, oxygen, and aluminum rose to the surface, forming the mantle and crust. Research indicates that differentiation began around 4.5 billion years ago, when the Earth was just forming from a protoplanetary disk. Gravitational forces played a crucial role in this process. The greater the mass of the element, the stronger its attraction to the center. As a result, iron and nickel, with their high density, gradually settled in the core, giving it its hot and metallic nature. The process of differentiation was not uniform and involved complex physical-chemical interactions. Molten rocks moved, mixed, and ultimately reordered. This process not only created the internal structure of the Earth, but also determined its geological activity. Thus, at the boundary between the mantle and the crustal layers, convective flows formed, which still control the movement of lithospheric plates. It is important to note that the temperature in the core reaches more than 4,000 degrees Celsius, which explains why iron and nickel elements remain in a liquid state under enormous pressure. Therefore, the differentiation of the Earth became the basis for the formation not only of geological structures, but also for the development of the atmosphere and hydrosphere. This was a process in which not only the physical properties of the materials, but also time played a role, creating a unique internal architecture of the planet. Scientific research using seismic waves has shown that the Earth's core has a radius of around 3,400 kilometers, and the mantle has a thickness of around 2,900 kilometers. These figures underscore the scale of the processes that took place and their influence on the formation of our planet. When the Earth was formed more than 4.5 billion years ago, heavy metals began to accumulate in its center, with iron and nickel being the primary elements. These elements, due to their high density, gradually descended to the planet's center, forming a powerful metallic core. This process can be visualized as a giant heart pulsating in the Earth's depths, composed of molten iron with temperatures reaching around 5,000 degrees Celsius. According to research conducted in the 2000s by scientists from Harvard University, this core consists of approximately 80% iron and 20% nickel. The constant pressure and temperature, significantly exceeding those on the surface, led to the formation of crystalline structures, giving the core unique physical properties. Around 3 billion years ago, the outer part of the core began to crystallize, resulting in the formation of the first solid iron core surrounded by a liquid outer layer. This process was driven by convection caused by heat released during the decay of radioactive elements such as uranium and thorium, present in the mantle and crust. The energy released in this process facilitated the movement of molten metal, which in turn influenced the formation of Earth's magnetic fields. However, even during the formation of the core, its pulsation and movement created conditions that would later become the basis for the formation of Earth's magnetic field. This process is not yet complete, and the core continues to evolve, affecting geological activity and climate conditions on the surface. Research indicates that the structure of Earth's core may have complex layers that are yet to be fully explored, and its dynamics remain a subject of active scientific debate. One notable example is the work of geophysicists who use seismic waves to study the internal processes of the Earth, allowing them to create models that show how heavy metals move within the core. Overall, the core of the Earth has a radius of around 1,300 kilometers, and its temperature is estimated to reach values comparable to those on the surface of the Sun. The cooling of Earth's surface was a long and complex process, reminiscent of a hot drink gradually cooling in a cup. Initially, when Earth was forming about 4.5 billion years ago, its surface was a molten magma ocean, with temperatures reaching thousands of degrees Celsius. This ocean was constantly in motion, and its waves, like those in a stormy sea, continually destroyed any previously formed solid crust. Gradually, as the temperature began to decrease, the first thin layers of solid crust began to form on the surface, much like the skin that forms on hot chocolate as it cools. This initial Earth crust was extremely fragile, composed of light minerals that could not withstand the intense conditions on the planet. For example, around 4 billion years ago, researchers like Dr. James Kerr from the University of California discovered that this early crust was constantly being destroyed due to volcanic activity and tectonic processes. With each new eruption or earthquake, this primary crust was repeatedly shattered, creating a sense of unstable equilibrium that persisted for millions of years. For instance, in the region of ancient continents like the Craton, where traces of these processes can still be seen today, it is possible to observe how remnants of the ancient crust were eroded and reformed. At this time, Earth's atmosphere was also undergoing changes. Hot gases released by volcanoes began to form the primary composition of the atmosphere, which was completely different from today's. This cooling and solidification process was not only physical, but also chemical. As a result of reactions with atmospheric gases and water formed on the surface, the first stages of new mineral formation began. For approximately 3 billion years, this fragile crust continued to transform, creating conditions for the emergence of life. But this process was always threatened by geological disasters. Data show that even today, in some places, such as mid-ocean ridges, volcanic eruptions continue, recalling those distant times when Earth was young and full of energy. The first solid crust of Earth, which emerged approximately 700 million years after the planet's formation, was a dark, basaltic landscape that was constantly torn apart and altered by volcanic activity. At that time, the planet was still young, and its surface was covered with extensive areas of solidified magma formed from volcanic eruptions. These basaltic formations created a contrast between black areas of solidified rock and bright, glowing fissures where magma rapidly rose to the surface, forming fiery fountains. These fissures, or rifts, were not just cracks in the crust, but true windows into the Earth's interior, allowing volcanoes to erupt lava and gases, forming new islands and land masses. During the formation of the crust, powerful tectonic movements occurred, leading to the creation of mountain ranges and valleys, resulting in a unique topography. The earliest oceans, formed by the condensation of water vapor from the atmosphere, gradually filled these depressions, creating conditions for the emergence of life. It is important to note that the crust was extremely thin. In some places, its thickness did not exceed 10 kilometers, making it highly susceptible to the influence of the magma beneath it. These volcanic eruptions not only shaped the physical structure of Earth, but also contributed to the formation of the atmosphere. Gases, such as carbon dioxide and water vapor, released during eruptions, created conditions for further development of climate systems. Massive lava flows filled valleys, creating large plateaus that we can observe today in some parts of the world, such as Iceland, where young crust is still subject to active volcanism. These geological processes occurred against the backdrop of a constant struggle between hot magma masses and cold oceans, creating a dynamic environment where everything was subject to change. Thus, the primary crust of Earth was not just a static shell, but a moving and evolving system, constantly changing under the influence of the planet's internal energy. A significant aspect of this process was that the eruptions occurring on this early surface led to the formation of the first minerals and rocks, which later became the basis for the development of more complex geological structures. As a result, diverse ecosystems began to appear on Earth, although life at that time was just beginning to awaken in the first water bodies formed on the surface. This interaction between volcanic activity and the aquatic environment became the catalyst for further planetary evolution and the appearance of the first forms of life. On the forming crust of the planet, covered with thousands of active volcanoes, there was unprecedented volcanic activity that shaped the Earth's appearance more than 3 billion years ago. These volcanoes spewed lava, gases, and ash, creating a tumultuous spectacle that can be compared to a majestic natural performance. Lava flows, reaching temperatures above 1,000 degrees Celsius, flowed across the surface, forming rivers of lava that spread over many kilometers, covering vast areas. Some of these rivers, such as the Kilauea River in Hawaii, continued to boil and erupt lava to this day, clearly demonstrating the persistence of this process. Magma fountains, erupting from the depths, rose hundreds of meters into the air, creating clouds of ash and gas that then settled on the surface, forming layers of volcanic sediment. On the horizon, fiery eruptions constantly sparkled, reflecting the eternal glow that created an atmosphere full of energy and dynamism. This activity never ceased, shaping the landscape of the young planet and contributing to the formation of new minerals and elements. Scientists like Dr. David Ferris, studying samples of ancient volcanic rocks dating back more than 3 billion years, found minerals such as olivine and pyroxene, which indicate the high temperatures and conditions that prevailed at the time. These minerals formed as a result of the crystallization of molten rocks that cooled on the surface or beneath it. Volcanic activity also contributed to the release of carbon dioxide gas and other gases, forming the primary atmosphere, which was extremely aggressive but necessary for the formation of future climatic conditions. These processes occurred endlessly, creating conditions for the further development of geological and biological systems that ultimately led to the emergence of life. Volcanic islands formed as a result of multiple eruptions, such as the islands of Tonga, became places where the first forms of life could potentially emerge. All this active activity not only shaped the landscape, but also created ecosystems that later became the basis for more complex biological forms. Early Earth's atmosphere was vastly different from the one we are familiar with today. When the planet was just beginning to form, it was enveloped in a thick, opaque gaseous layer created by intense volcanic activity. Gases emitted from Earth's interior formed a heavy, toxic atmosphere that was essentially the planet's first breath. This cloud of gases blocked out sunlight, creating dark, gloomy conditions. Volcanic activity, which occurred around 3.5 billion years ago, released enormous amounts of carbon dioxide, water vapor, and other volatile compounds that filled the young atmosphere. These gases, cascading from volcanoes, formed dense clouds and created conditions in which the life we know today would have been impossible. This period can be imagined as a hellish furnace where temperatures reached critical levels and the air was saturated with poisonous vapors. Despite the extremely unfavorable conditions for life, it was this atmosphere that provided the impetus for the formation of the first molecules, which later became the basis for biochemical processes. Scientists such as Professor James Cameron from the University of California believe that such conditions could have facilitated the formation of organic compounds in deep oceans, which in turn laid the foundation for the emergence of the first forms of life. Volcanic eruptions during this time were not just destructive, but also vital for shaping the planet's environment. Each eruption spewed tons of ash and gas, forming the landscape and climate as we know it today. This toxic atmosphere was not just an empty space, but a complex system of interactions that ultimately led to the emergence of life. Scientists continue to study this period to understand how the first biochemical reactions arose, but one thing is certain: this dark, heavy atmosphere, filled with poisonous gases, was the first stage on which the drama of life's appearance on Earth unfolded. On the early Earth, there was a genuine meteorite bombardment, with celestial bodies of various sizes, from small meteorites to massive asteroids, continuously crashing onto its surface. Approximately 3.5 billion years ago, during what is known as the Late Heavy Bombardment period, Earth was subjected to attacks from objects averaging several kilometers in diameter. The sky was crisscrossed with the bright trails of falling objects, creating the appearance of a constant cosmic war. During one such impact, likely around 4 billion years ago, a collision with a body the size of Mars occurred, which, according to scientists, is believed to have led to the formation of the Moon. This event, known as the giant impact hypothesis, not only altered the landscape of Earth, but also its orbital characteristics. Each impact left behind new craters, and the surface of our planet was constantly changing, as if an artist with boundless inspiration were painting on a canvas of ice and stone. For example, the Vredefort crater in South Africa, formed around 2.5 billion years ago, has a diameter of over 100 kilometers and is considered one of the largest impact craters on Earth. This meteorite activity was tens of times more intense than it is today, as Earth at that time lacked a protective magnetic field that could have at least partially deflected this cosmic bombardier. Scientific research shows that during the first 500 million years of the planet's existence, meteorites fell on its surface at a rate of up to 100 large objects per year, creating unimaginable conditions for the formation of the primary atmosphere and possibly the first forms of life. This constant cosmic assault not only changed the physical state of the planet, but also contributed to the complex chemical reactions between surface minerals and elements, creating conditions for further evolution. Looking at the surface of the Moon, dotted with craters, one can easily imagine what the young Earth looked like, where new battles with celestial bodies took place every day, filling the history of the planet with events that ultimately led to the emergence of life. Approximately 4 billion years ago, Earth experienced a period known as the Late Heavy Bombardment. During this time, the number of asteroids striking the planet increased dramatically. Scientists believe that in this period, which lasted for several hundred million years, celestial bodies the size of modern countries like Australia or even Europe were falling onto Earth's surface daily. These collisions resulted in catastrophic events. The impact of such massive objects would melt the already solidified crust, creating enormous craters. For example, the Vredefort crater in South Africa, which formed around 2 billion years ago, has a diameter of over 100 kilometers and is considered one of the largest impact craters on the planet. However, During the late heavy bombardment, such collisions were commonplace. Astronomers estimate that during this period, Earth could have collided with asteroids and comets several kilometers in diameter every few million years. These impacts not only heated the planet, but also contributed to the formation of an atmosphere rich in carbon dioxide and water vapor, which was a crucial step in the emergence of life. During this time, not only were craters formed on Earth's surface, but new geological features like volcanoes also emerged. Scientists such as Dr. John Candy from the University of London assert that it was the intense bombardment that created conditions favorable for the emergence of the first forms of life. In this chaos, oceans were also formed, and the impacts of asteroids could bring organic molecules that later became the basis for biochemical processes. Eventually, as the intensity of the bombardments decreased, Earth began to stabilize, and conditions for more complex forms of life began to emerge on its surface. During this period of meteorite bombardment of Earth, which lasted approximately from 4 billion to 3.5 billion years ago, celestial bodies such as icy comets and asteroids played a key role in the formation of the planet's water reserves. Studies indicate that water-rich asteroids could deliver significant volumes of this resource to Earth. For instance, comets consisting of 90% ice would collide with the planet, releasing vast amounts of water in the form of vapor, which contributed to the formation of the primary oceans. Scientific data suggests that, according to estimates, more than 30% of the water on Earth could have been brought by meteorite bombardment. Astronomers such as Dr. Emily Lakdawala from the University of California note that comets like Halley's Comet not only impacted Earth, but also enriched its atmosphere with water vapor, which became the basis for future precipitation. This process did not occur instantaneously, but gradually. Drop by drop, meteorite by meteorite, millions of cosmic messengers fell onto the planet's surface, carrying the precious liquid essential for life. It is important to note that over millions of years, various meteorite showers, which constituted a significant part of Earth's early history, created conditions for the formation of stable water bodies. As a result of these interactions, by 4 billion years ago, Earth already had sufficient water reserves to form oceans, marking a new era in the planet's history. It is worth noting that the process of ocean formation was not only due to direct comet impacts, but also due to thermal reactions arising from collisions, where water bound in minerals was released as a result of heating. For example, researchers from the German Aerospace Center, under the leadership of Dr. Simon Gatz, found that some water-containing minerals could decompose at high temperatures, also contributing to the increase in the volume of water on the planet's surface. Thus, meteorite bombardment not only created conditions for the formation of oceans, but also became a crucial factor in providing the first forms of life with the necessary resources. As a result, by the time Earth finally stabilized, it already had significant water reserves, which became the foundation for the further development of life in various forms. The process of forming the primary oceans on Earth was long and complex. From the moment the planet began to cool, water vapor in its atmosphere, formed as a result of volcanic activity and comet impacts, gradually started to condense. This process did not happen instantaneously. Over millions of years, as the surface temperature of Earth decreased, water vapor turned into droplets that, like enormous, long-lasting rains, settled on the planet's surface. These rains did not last for days or years, but spanned thousands of years, gradually filling lowlands and forming primary water bodies. One of the key stages of this process began approximately 3.5 billion years ago, when the temperature dropped to a level that allowed water to remain in a liquid state. Over many years, water began to fill in the depressions in the terrain that had formed due to tectonic activity, erosion, and other geological processes. Water, mixing with minerals and elements present on the surface, created suitable conditions for the emergence of life. This water was not calm, it mixed, became part of early ecosystems, and also served as a medium for chemical reactions necessary for the appearance of the first living organisms. It was during this period that large masses of water began to form on Earth, which later became oceans, and their impact on the climate and biosphere was immense. Gradually, as the planet continued to cool, oceans became more extensive, and their composition became more diverse, creating unique conditions for the evolution of life. Ultimately, the formation of the primary oceans became one of the key moments in Earth's history, opening the way for the appearance of multicellular organisms, which played a crucial role in the further development of the biosphere. The first appearance of rain on Earth occurred approximately 3.5 billion years ago, and this event was far from tranquil. Instead of the clean water we are accustomed to today, the initial rainfall consisted of a mixture of acids and various chemical compounds, such as sulfuric and carbonic acids, which resulted from volcanic activity and the release of gases into the atmosphere. These rains poured down onto the scorching surface of the planet, with temperatures exceeding hundreds of degrees Celsius. Imagine a continuous downpour, with a fierce sizzling sound falling onto molten lava flows, causing the formation of clouds of steam that quickly rise into the air. In this context, the sky filled with black clouds is a spectacle of elemental struggle. The fiery surface of Earth and the acidic rains falling from the heavens create an impression of a genuine battle. The acidic precipitation, acting on minerals and rocks, gradually formed the primary water bodies, rich in chemical elements that became the basis for future biochemical processes. Scientific research indicates that such rains could create conditions favorable for the synthesis of organic molecules necessary for the emergence of life. For example, laboratory experiments conducted by scientists such as Stanley Miller in 1953 showed that under the influence of electrical discharges and water vapor, amino acids, which are the building blocks of proteins, could be synthesized. These first rains not only altered the landscape of Earth, but also served as a catalyst for the formation of complex organic compounds. The pools and water bodies formed as a result of the rains acted as natural reactors, where chemical reactions necessary for the emergence of the first living organisms took place. Thus, the acidic rains not only played the role of a climatic phenomenon, but also became a significant stage in the evolution of our planet. The first bodies of water on early Earth were vastly different from what we see today. Over 3 billion years ago, as our planet was just beginning to take shape, oceans were hot and rich in minerals. These initial water bodies likely had temperatures around 100 degrees Celsius, which facilitated their rapid evaporation and the formation of a dense water vapor layer in the atmosphere. The water in these oceans was not clear, but rather had a murky, possibly greenish or brownish hue due to the high concentration of dissolved minerals and organic compounds released by volcanoes. These water bodies teemed with simple life forms, but their ecosystems were highly unstable. Continuous volcanic activity caused the boundaries of these seas to constantly shift, with new land areas rising and old ones being submerged. For instance, on the territory of modern-day Greenland, where such water bodies once existed, scientists have found remnants of ancient marine deposits dating back to around 3 billion years ago. These deposits indicate fluctuations in sea level caused by tectonic processes. There were even instances where entire water bodies could disappear, leaving behind only dried-up salt deposits. In such conditions, life was just beginning its journey, and each new generation of organisms had to adapt to the changing environment. These primary oceans served as the cradle for the first living organisms, but their instability and constant changes created conditions that could both sustain life and pose a threat to it. Scientists like Dr. John L. Wilson from the University of Cambridge emphasized the significance of these early water bodies for understanding the evolution of life on Earth. They also note that the conditions in which life originated were as diverse and complex as they were, raising many questions about how this process occurred. As a result, these primary oceans not only witnessed, but also participated in the formation of the first ecosystems, which later became the foundation for more complex forms of life. In the primary oceans, remarkable chemical reactions took place, which can be compared to the work of a giant natural laboratory. Water interacted with minerals in the Earth's crust, dissolving various elements and compounds to create a complex chemical broth. This broth consisted of numerous components that mixed, reacted with each other, and formed new substances. The atmosphere, containing gases such as carbon dioxide and ammonia, also actively participated in these reactions, contributing to the formation of organic molecules. For instance, the interaction of water with minerals containing iron and magnesium could lead to the formation of various oxides and hydroxides, which in turn altered the chemical composition of water and created new conditions for further reactions. In this context, oceans can be seen as dynamic ecosystems where thousands of different chemical processes occurred at any given moment. These reactions were not merely random. They laid the foundation for future life, creating conditions in which simple organic molecules could arise. As these molecules became more complex, they formed the basis for the emergence of the first cells. Scientists like John Watson and Francis Crick later discussed how such chemical interactions could have led to the appearance of life, although at that time it was just the beginning. The primary oceans thus served as a testing ground where nature sought different paths to create life. These processes, occurring over millions of years, paved the way for the biological diversity we observe today. For example, in the 31st epoch of Earth's history, known as the Archean, oceans already contained primitive single-celled organisms that began to evolve. These primary forms of life, which emerged as a result of complex chemical reactions, became the predecessors of all modern living beings, from bacteria to plants and animals. Hydrothermal sources on the floor of primary oceans are among the most mysterious and fascinating natural phenomena on our planet. These oases of heat and chemical activity form as a result of geothermal heating, when hot water, rich in minerals, erupts from cracks in the ocean floor, creating underwater chimneys. These chimneys are vertical tubes that can reach several tens of meters in height, from which streams of dark, mineral-rich water erupt, with temperatures that can exceed 300 degrees Celsius. For example, in the area of the mid-oceanic ridge, which stretches over more than 16,000 kilometers, there are numerous such sources. Unique ecosystems form around them, where life thrives despite extreme conditions, high temperature, pressure, and lack of sunlight. Organisms such as tube worms, which can reach lengths of over 1 meter, inhabit these places and have a unique symbiotic relationship with bacteria that can convert sulfur into energy. These bacteria, in turn, form the basis of the food chain, making hydrothermal sources true islands of life in the dark depths of the ocean. The contrast between the hot water emerging from the sources and the cold surrounding ocean water creates a sharp boundary on which complex chemical reactions occur, leading to the formation of minerals such as pyrite and chalcopyrite. These minerals, expelled into the ocean, create not only spectacular underwater landscapes, but also influence the composition of ocean water. Studies conducted in the late 1990s showed that places like the hydrothermal sources of Elysium in the Pacific Ocean can contain up to 30 different elements, including gold and silver, making them of interest to researchers and geologists. These sources not only attract the attention of scientists, but also serve as key sites for studying the origin of life on Earth, as conditions similar to these could have given rise to the first simplest organisms, thanks to the unique chemistry and energy available in such ecosystems. The formation of the first continents began around 2 billion years ago, when sections of lighter crust began to float on the surface of the mantle. These early continents were small fragments of land that gradually gathered together, creating small archipelagos. Imagine a young, unstable world where land masses constantly changed shape under the influence of geological processes such as volcanism and plate tectonics. At this stage, for example, The Proterozoic era was characterized by active volcanic activity. Volcanic islands appeared and disappeared, and geysers spewed steam and hot water, creating a bubbling atmosphere, quite unlike the calm, vegetation-covered continents we know today. These lands were smaller in size and lacked a stable ecosystem. Unlike today's continents, where vegetation and animal life have developed into complex ecosystems, the first continents were almost barren, devoid of the life we are accustomed to. For instance, in the area of today's Australia and Greenland, the first continental blocks were forming, which later became the basis for the formation of large continents. This was an era when geological processes were working at full capacity. Earthquakes and volcanic eruptions formed new landscapes, causing continents to contract and expand. The formation of supercontinents like Rodinia occurred as a result of the merging of these small landmasses, creating temporary continents that existed for only millions of years before breaking apart into smaller fragments. These processes resulted in the surfaces of the first continents being highly dissected and diverse, with high mountains and deep valleys that were later filled with water, creating seas and oceans. Volcanic activity, as evidenced by samples taken from deep wells, was particularly intense, leaving behind traces of lava and sedimentary rocks, indicating a tumultuous history of the formation of the Earth's crust. Over billions of years, these processes continued to reshape the planet, resulting in the continents we know today. But the first continents were merely small, dynamic islands, constantly changing under the influence of natural forces. Archaeologists and geologists, such as Dr. Linda White from the University of California, conducted research on these early formations, which has helped to better understand the processes underlying continental drift. Each discovery reveals a little more about how our planet formed and continues to evolve. In the early Earth, tectonic processes occurred with incredible intensity, making its surface a true mosaic of mobile elements. At that time, the Earth's crust, broken into fragments, was constantly moving, colliding and spreading, like a giant puzzle that never stopped changing. This process was driven by the planet's high internal heat, which was several times greater than today. For instance, in the first billion years of Earth's existence, the temperature inside the planet reached around 1,000 degrees Celsius. This heat caused convection currents in the mantle, which pushed crustal fragments against each other, leading to mountain building and earthquakes. As a result, continents formed and broke apart, creating conditions for the emergence of various geological structures such as mountain ranges and oceanic trenches. These processes occurred over billions of years, starting with the formation of Earth around 4.5 billion years ago. During this period, for example, the first continents, such as Rodinia, which existed around 1 billion years ago, were formed. These continents were significantly smaller and more fragmented than we are accustomed to seeing today. They periodically merged and split, creating diverse ecosystems and climatic conditions. Tectonic movements also triggered volcanic activity, which contributed to the formation of new lands and changes in climate. For example, volcanic activity resulted in the formation of islands in the Pacific Ocean, which later became home to unique ecosystems. The constant changes on the planet's surface created an endless cycle of formation, destruction, and reformation of landscapes, which in turn influenced the development of life. Such a dynamic process of crust formation was much more active than it is now, when the driving forces of tectonics have significantly weakened and the surface of the Earth has become more stable. As a result of tectonic activity on early Earth, conditions were created for the appearance of the first forms of life, such as single-celled organisms, which began to develop around 3.5 billion years ago. Subduction is a process in which one tectonic plate slowly descends beneath another, returning to the Earth's mantle. For example, when an oceanic plate, such as the Philippine plate, encounters a continental plate, such as the Eurasian plate, the denser oceanic plate begins to subduct. This process resembles a gigantic conveyor belt, where surface materials gradually return to the planet's interior, where they are subjected to high temperatures and pressures. Subduction zones, such as the Japanese and Cascade zones, become areas where powerful earthquakes and volcanic eruptions occur, but the process of subduction itself is slow. Over millions of years, a plate can subduct to a depth of up to 70 kilometers into the mantle, where temperatures can reach thousands of degrees Celsius. This process does not happen overnight. The rate of subduction is only a few centimeters per year. This creates a sense of geological tranquility, while beneath the Earth's surface, a powerful struggle of matter unfolds. Research shows that in the process of subduction, not only does subduction occur, but materials are also recycled, leading to the formation of magma. For example, the subduction of the Nazca Plate under the South American Plate resulted in the formation of the Andes, the longest mountain range on the planet, with some peaks exceeding 6,000 meters in height. Subduction also activates volcanic activity. As a result of this process, volcanoes like Lassen Peak in Utah, which is approximately 2,300 meters high, are formed. This volcano was created because material returning to the mantle melts and rises, creating pressure that ultimately leads to an eruption. It is important to note that subduction not only shapes landscapes, but also influences climate, as volcanic eruptions can release large amounts of ash and gases into the atmosphere, altering weather conditions. For example, the eruption of Krakatoa in 1883 caused a global decrease in temperature, affecting crop yields in various regions of the world. This process also affects ecosystems, as it creates new habitats and changes existing ones, providing conditions for the survival and evolution of various species. Subduction, in essence, is not just a geological process, but a powerful mechanism that influences life on Earth at many levels. As a result of this process, not only are mountain ranges and volcanoes formed, but the compositions of oceans are also altered, which in turn affects marine flora and fauna. As a result of tectonic processes that occurred on early Earth around 2.5 billion years ago, the first mountain ranges were formed. Collisions between different sections of the crust led to some plates rising while others sank, creating characteristic folds and mountain ranges. At this stage, when the planet was still young, the mountains did not have the majestic forms we see today. Instead, they were low, sharp ridges of dark volcanic rock, as if squeezed out of the Earth's interior. These primitive formations were far from the high peaks we see today, and their height was small, but they still represented the power of the geological forces at work during that period. Considering the lack of erosion characteristic of modern mountains, one can imagine how the newly formed peaks looked in their original state. There were no rivers or glaciers to erode their contours, only wind and rain slowly smoothing the newborn summits. This process was extremely slow, with mountains growing and changing over millions of years, and each new wave of plate collision giving them a unique shape. For example, the formation of the Urals, which occurred around 300 million years ago, involved the collision of the ancient continent Laurasia with Gondwana, leading to their uplift. These mountains essentially bore witness to the changes in the planet itself. They preserved the traces of those tectonic processes that defined the appearance of Earth in its early history. The formation of mountain ranges at that time was a significant stage in the geological evolution that laid the foundation for the subsequent diversity of landscapes and ecosystems. Over centuries, these mountains were subjected to various climatic conditions, ultimately leading to the formation of more complex geological structures. It is important to note that at this stage of mountain formation, there was no vegetation yet that could conceal their original features. Each new batch of volcanic lava erupting onto the surface added to the existing samples, creating unique geological layers that can still be observed today. Volcanic activity also contributed to the formation of various minerals that would later be used by humanity. Taking all these factors into account, it can be said that it was during this period that the long and complex history of landscape formation began. which would later become home to countless living beings. Over the course of hundreds of millions of years, the atmosphere of early Earth underwent significant changes, influencing the conditions in which life developed. Initially, when the planet was still forming, the atmosphere was dense and toxic, composed of gases emitted by volcanoes that formed a shield around the young world. Over time, due to active geological processes, the evolution of this primary atmosphere began. Volcanic activity, billions of years ago, released enormous quantities of water vapor, carbon dioxide, and other compounds, which gradually condensed to form oceans. These oceans not only served as a source of water, but also acted as a catalyst for chemical reactions that altered the composition of the atmosphere. Gradually, the sky began to lighten, and the density of the atmosphere decreased, creating more comfortable conditions for the formation of more complex molecules and, ultimately, for the emergence of life. This slow process was akin to the planet's breathing, a deep inhale when gases rose into the air, and a slow exhale when they dissolved in the oceans. During this time, atmospheric conditions changed in such a way that more stable climatic conditions became possible. These changes occurred slowly, spanning not just one generation, but millions of years, allowing various forms of life to adapt to new conditions. Approximately 2 billion years ago, with the onset of the oxygen catastrophe, another revolution in the composition of the atmosphere occurred, as a significant amount of oxygen began to accumulate in the atmosphere, made possible by the photosynthesis of cyanobacteria. This process not only transformed the atmosphere itself, but also opened new horizons for life, creating conditions for the appearance of multicellular organisms. As a result, the atmosphere of Earth evolved into the one we know today, where against a blue sky float clouds and life flourishes in myriad forms. The process of weathering occurring on Earth is a complex and multifaceted mechanism that shapes our atmosphere and landscape. Every time rain falls on rocks, it does not merely wet them, but enters into chemical reactions, extracting certain elements. For instance, water containing carbonic acid, formed by the interaction of carbon dioxide with raindrops, dissolves calcite in limestone, leading to the formation of carbonates. This process, which can be likened to a slow dance between water droplets, rocks, and air, gradually alters the planet's appearance as dissolved minerals are transported by water flows and then deposited in other places. Thus, weathering affects the composition of soil and, consequently, the ecosystems that depend on these changes. For example, in tropical rainforests, where rainfall is abundant, rapid weathering leads to the formation of more acidic soils, which in turn influences the types of plants that can grow there. Conversely, in arid regions such as the Sahara Desert, weathering occurs more slowly and soils remain more alkaline, also determining the local flora. It is important to note that weathering is not limited to chemical processes. Physical weathering, such as freezing and thawing, also plays a significant role in the breakdown of rocks. For example, when water penetrates cracks in rocks and freezes, it expands, causing further cracking and rock destruction. This physical weathering can create extraordinary geological formations, such as pillars and arches, which we see in national parks, like the Grand Canyon. Therefore, weathering is an integral part of the global geochemical cycle that occurs wherever water meets rock. This cycle not only changes the physical characteristics of Earth, but also influences the climate, as the altered composition of the atmosphere can lead to changes in temperature and rainfall levels. Additionally, scientists such as Dr. Jonathan Martin from the University of California are studying the impact of weathering on the carbon cycle and its connection to global warming, emphasizing that weathering, as a natural process, can play a role in regulating climatic conditions on the planet. It is no surprise, then, that this dynamic process, occurring over millions of years, remains a focus of geological research and climate science. The formation of the primary ozone layer in the upper layers of the atmosphere occurred approximately 2.5 billion years ago. This process was caused by the interaction of solar ultraviolet radiation with oxygen molecules that were produced as a result of photosynthesis by the first living organisms. Ultraviolet rays broke down the oxygen molecules into atoms, which then combined with other oxygen molecules to form ozone. This ozone began to accumulate in the stratosphere, creating an invisible shield that gradually formed high above the Earth's surface. Initially, the concentration of ozone was low, but over time it increased, and the ozone layer became denser. Scientific research shows that at the peak of ozone layer formation, its concentration could reach levels that effectively blocked up to 90% of harmful ultraviolet radiation. This process became critically important for the protection of developing life forms on Earth. Without the ozone layer, ultraviolet radiation could have destroyed DNA molecules, making life on the planet's surface practically impossible. Thus, the formation of the ozone layer became not only a significant geochemical event, but also a foundational moment that laid the groundwork for future biological evolution. It is important to note that this process continued for millions of years, and its effects are still felt today as the ozone layer continues to protect the Earth from dangerous solar rays. Currently, scientists are still studying its changes and impact on the climate, which underscores the relevance of this issue even in our time. There are various methods of studying the ozone layer, including satellite observations and ground measurements, which allow for tracking its condition and predicting future changes. These data have helped determine that at the end of the 20th century, due to international efforts to limit the use of freons and other ozone-depleting substances, the ozone layer began to recover, which is a promising sign for the planet's ecology. The atmosphere of Earth changed not only on its surface, but also within its depths, in the primary oceans, where an extraordinary process began that can be compared to a chemical dance. Simple molecules, like participants in a ballet, combined to form more complex chains. This process occurred billions of years ago when Earth was young, and its oceans were filled with chemical diversity. In conditions resembling a real laboratory, the simplest elements such as carbon, hydrogen, oxygen, and nitrogen interacted with each other, forming more complex structures. Energy from lightning, which gave life to this chaos, and ultraviolet radiation penetrating the water served as a catalyst for these reactions. Around this energy, a real spectacle unfolded. Molecules combined, broke apart, changed their forms, creating a variety of compounds. This process was not random. It resembled a complex symphony where each note played an important role in the formation of new compounds. Often, such reactions occurred in hot springs where temperatures could reach hundreds of degrees Celsius, providing the necessary energy for the creation of more complex molecules. For instance, in such conditions, chains capable of self-replication and, ultimately, evolution into more complex forms of life could form. Research shows that it was precisely in these primary broths that processes began that later led to the emergence of the first organisms. It is important to note that in this chaos of simple molecules, order gradually emerged due to constant interactions and changes, eventually becoming the basis for life as we know it. These transformations occurred under the influence of various factors, including temperature fluctuations and the composition of the oceans, which could change, creating new opportunities for chemical reactions. Scientists studying this topic note that it was precisely in these conditions, when simple molecules began to interact, that life began, and this process can be seen as the beginning of a long path of evolution. As a result of numerous chemical reactions occurring in the oceans, compounds arose that later became the basis for the creation of the first cells. Thus, the primary oceans became not just bodies of water, but places where life began and where this chemical symphony took place, leading to the formation of complex molecules that eventually became the basis for all living beings on Earth. The RNA world hypothesis offers an intriguing perspective on the pre-biological stages of evolution. where RNA molecules could have been the first candidates for the role of living entities, balancing on the border between non-living and living matter. Unlike DNA, RNA possesses a unique ability to simultaneously store genetic information and function as catalysts for chemical reactions. This means that a single molecule can both store information about protein synthesis and accelerate this process, making RNA an ideal candidate for the earliest forms of life. This hypothesis was proposed in the early 1990s by a group of scientists led by Carol M. F. Bailey and Eric G. Craig, who conducted experiments demonstrating that RNA molecules could catalyze reactions similar to enzymes, opening new horizons in understanding the origin of life. These molecules likely emerged in the conditions of ancient oceans, where they could form from simple organic compounds, such as nucleotides. It is important to note that this process was not random, but a result of chemical evolution, in which RNA molecules could compete and evolve, much like modern organisms. In experiments conducted in 2003, scientists from the Molecular Biology Institute at the University of Texas at Austin showed that RNA molecules can spontaneously form under certain conditions, confirming their natural origin. These molecules, as the first candidates for living entities, would be capable of self-replication, which is a key aspect of life. Based on these findings, it can be hypothesized that RNA could perform a dual function, providing it with a significant advantage in the process of natural selection. For example, in 2006, scientists created artificial RNA molecules that could synthesize other RNA molecules, thereby demonstrating the principle of self-replication. This discovery was a significant step in understanding how some molecules could have become the basis for more complex forms of life. RNA, with its ability to catalyze and store information, could serve as a bridge between non-living and living matter, highlighting the importance of studying this hypothesis for understanding the origin of life on Earth. For instance, in 2009, experiments conducted by scientists showed that under certain conditions, RNA molecules can form structures resembling cellular organelles, adding an additional layer of complexity to the process of evolution. The formation of the first cellular membranes was a pivotal stage in the evolution of life on Earth, and this process can be traced back to 1 billion years ago, when the planet was inhabited only by simple molecules. In the aqueous environment, lipid molecules with hydrophobic and hydrophilic ends began to spontaneously organize into structures that later became known as lipid bilayer membranes. The hydrophilic ends of these molecules sought to interact with water, while the hydrophobic ends repelled it. This intriguing process led to the formation of microscopic bubbles, which can be envisioned as the thinnest of envelopes, separating the internal contents from the surrounding environment. These bubbles, composed of 2 layers of lipids, created a protected space in which more complex chemical reactions could occur. It was here, in these microenvironments, that the conditions for the emergence of the first biochemical processes necessary for the formation of more complex molecules, such as proteins and nucleic acids, arose. Studies conducted in the 12th century by scientists like Lawrence Allen and his team showed that membrane bubbles can form spontaneously even in simple conditions, thus supporting the hypothesis that life could have originated in such primitive systems. This discovery underscores the significance of the separation of internal and external space, which is the basis for the existence of cells and, consequently, all life. The structural organization of these membranes also created conditions for the formation of the first cells capable of metabolism and replication. It is important to note that such membranes became the precursors of modern cellular envelopes, which perform numerous functions, including protection, transport of substances, and signal transmission. These primary cellular membranes not only provided physical protection, but also created conditions for the emergence of complex biochemical pathways, which in turn contributed to the further evolution of living organisms. Thus, the process of forming cellular membranes became the cornerstone for the emergence of life itself, opening the way to multicellular organisms and ecosystems that we know today. Based on these observations, it becomes clear that it was precisely this mechanism of molecular self-assembly that laid the foundation for the existence of cellular life. The study of the origin of the first protocells is like observing the birth of the whisper of life in the silent void of ancient oceans. Approximately 3.5 billion years ago, under conditions favorable for chemical reactions, molecular systems began to form, gradually acquiring properties characteristic of living organisms. This was not a one-time process, but a slow, gradual transition from simple chemical compounds to more complex structures capable of self-replication. At the initial stage, compounds such as amino acids and nucleotides began to combine into more complex molecules. Thus, in the primary atmosphere of Earth, rich in carbon dioxide, water vapor, and methane, reactions occurred that led to the formation of the first organic compounds. For example, in 1953, in the famous experiment by Stanley Miller, amino acids were obtained from simple chemical substances, confirming the possibility of organic synthesis under conditions similar to early Earth. These molecules, in turn, formed more complex structures that could exchange substances with the surrounding environment, reacting to changes in the chemical composition of water. Gradually, over millions of years, these systems began to develop a mechanism of self-replication, which became a critical step in the appearance of the first protocells. Emerging as a result of random combinations, such molecules could copy themselves, transmitting information to the next generation. This manifested in the fact that under certain conditions, they could create copies of their structures, which became the basis for further evolutionary processes. At the same time, such molecules reacted to external factors, changing their behavior depending on the chemical environment, which added an element of adaptation. Thus, the boundary between the non-living and the living gradually blurred, and life began to manifest in its most primitive form. This process can be compared to how a quiet whisper in the ocean of chemical reactions gradually turns into a melody, complex, multi-layered, and full of life. These early molecules, like music, began to interact, forming ever more complex networks of chemical reactions that laid the foundation for living organisms. As a result, by 2 billion years ago, we observed the first single-celled organisms living in aquatic ecosystems, endowed with properties that were previously only characteristic of chemical compounds. Stromatolites represent one of the oldest forms of life on Earth, with an age exceeding 3 billion years. These layered structures are formed by the activity of microorganisms, primarily cyanobacteria, which inhabit shallow seas. These tiny organisms, measuring only a few micrometers, are capable of photosynthesis, enabling them to not only survive, but also actively alter the composition of the atmosphere by releasing oxygen. Stromatolites appear as low mounds that grow slowly, layer by layer, forming a kind of book of life's history. Each layer of stromatolite can testify to various environmental conditions over millions of years. For example, in Western Australia, some of the most famous stromatolites, estimated to be around 3 billion years old, continue to form in conditions similar to those that existed in ancient oceans. These structures can reach heights of several meters, with their shape varying from small elevations to large masses visible on the surface. Stromatolites also serve as important evidence of the first ecosystems on the planet, where microorganisms interacted with each other, forming complex biological communities. For instance, in some modern stromatolites, researchers have found diverse types of bacteria that coexist and complement each other, creating unique conditions for life. These ancient formations are not just of geological significance. They provide scientists with the opportunity to study how life on Earth evolved and adapted to changing conditions over billions of years. Stromatolites serve as important indicators of ecological changes, allowing us to understand how microorganisms could influence the global climate system. Specifically, Stromatolites demonstrate how processes of sediment formation occurred in early oceans and what influence microorganisms had on the formation of the Earth's crust. Today, stromatolites continue to exist in some ecosystems, such as lagoons in Australia and the Bahamas, where they form unique ecosystems, providing a habitat for numerous other organisms. They are not just historical artifacts, they are living testimonies to the multi-billion-year history of life on our planet. Ancient cyanobacteria, which appeared on Earth more than 3 billion years ago, were the first organisms capable of photosynthesis. This process, in which cyanobacteria used solar energy to synthesize organic compounds, transformed the appearance of our planet. Cyanobacteria, such as the genus Stromatolite, possessed chlorophyll and other pigments that allowed them to absorb light rays. During photosynthesis, they extracted carbon dioxide from the atmosphere and water, producing glucose and oxygen. Scientists believe that it was cyanobacteria that initiated the oxygen boom on Earth, which occurred around 2.5 billion years ago. This historical event is known as the Great Oxygenation Event. As a result of the intense release of oxygen, which initially accumulated in the oceans, the atmosphere began to become saturated with oxygen, leading to significant changes in the chemical composition of the atmosphere and contributing to the emergence of aerobic, oxygen-dependent organisms, such as animals. The process of photosynthesis in cyanobacteria was revolutionary because, for the first time, living organisms began to actively alter their environment, creating conditions for the existence of more complex forms of life. These microscopic creatures, by creating oxygen, not only changed the atmosphere, but also supported ecosystems that subsequently developed on the planet. For example, cyanobacteria became the main producers of food in the oceans, forming the basis for food chains. Research shows that cyanobacteria were the main participants in the carbon cycle and played a key role in maintaining life on Earth. Microscopic organisms that convert light energy into chemical energy slowly but surely changed not only the atmosphere, but also the entire appearance of the planet, creating conditions for the emergence of biodiversity. As a result of their activity, the planet became more suitable for life and led to the appearance of new forms of life. The change in the concentration of oxygen in the atmosphere also gave rise to the formation of the ozone layer, which protected life on the surface from harmful ultraviolet radiation. Thus, cyanobacteria, by absorbing solar light, became not only the first phototrophs, but also the founders of the oxygen era on Earth, which played a key role in the evolution of life. The oxygen event that occurred on Earth more than 2 billion years ago was one of the most significant turning points in the history of our planet. At that time, oxygen produced by photosynthetic organisms such as cyanobacteria began to accumulate in the atmosphere. This process can be imagined as a gradual change in the color of the sky, from the initial yellowish-brown, symbolizing the absence of free oxygen, to the clear blue sky that we see today. With each new wave of photosynthesis, each cyanobacterium, absorbing sunlight and carbon dioxide, released oxygen into the water and atmosphere, changing the chemical composition of the oceans. When the oxygen level began to rise, the oceans became saturated with oxygen, leading to the formation of new minerals such as iron oxides, creating sedimentary rocks that we can observe today in places like the iron ore deposits in Mesopotamia or Australia. However, this accumulation of oxygen was a double-edged process. For most of the existing forms of life at the time, such as anaerobic microorganisms, oxygen was toxic. These organisms could not survive in conditions where the oxygen level exceeded a certain threshold, leading to mass extinctions. Nevertheless, this same oxygen opened up new evolutionary possibilities for other organisms. Aerobic organisms that could use oxygen to obtain energy began to develop, eventually leading to the emergence of multicellular life. This transition became the foundation for further evolution, allowing the appearance of complex forms of life and, ultimately, humans. The ability to produce and use oxygen opened up new ecological niches that were filled by animals and plants, leading to a rapid increase in the diversity of the biosphere. As a result, by the time oxygen became the main component of the atmosphere, Earth had already begun to actively transform, with its oceans and atmosphere becoming habitats for new, more complex forms of life. The accumulation of oxygen in the atmosphere acted as a catalyst for the formation of the ecosystems that we know today. Red-banded iron formations, which formed as a result of the oxygenation of oceans, are unique geological records of the transformation of our planet. These rocks, found in places like Australia and South Africa, have distinctive red bands composed of alternating layers of iron and silica. The formation of these layers began approximately 2.5 billion years ago, when the level of oxygen in the atmosphere began to significantly increase due to photosynthetic bacteria such as cyanobacteria. Their activity caused iron, previously dissolved in the oceans as ions, to react with oxygen, forming iron oxides like hematite and magnetite, which then precipitated onto the ocean floor. These precipitates accumulated, creating layered deposits that eventually became the red-banded iron formations. It is important to note that the oxygen released by cyanobacteria not only facilitated the formation of these minerals, but also altered the chemical composition of the oceans, creating conditions for the emergence of complex ecosystems that we observe today. Essentially, these rocks serve as a geological chronicle, inscribed in stone, preserving key events in Earth's history. Scientists like Dr. Alison Hazelton from the University of Leeds study these samples to better understand how the oxygen catastrophe influenced the development of life on the planet. They analyze the ratio of oxygen and carbon isotopes in these layers, allowing them to reconstruct the conditions under which these geochemical changes occurred. For example, data from samples found in the supercontinent shield area indicate that the oxygen level in the atmosphere could reach 30%, which is significantly higher than current values. Therefore, red-banded iron formations are not just geological formations, but actual archives that contain information about how life on Earth adapted to changing conditions. They help us understand how the oxygenation of oceans contributed not only to the development of multicellular organisms, but also to the appearance of the first animals and determined the further evolution of the biosphere. The snowball Earth hypothesis describes a period in the history of our planet when it could have been almost entirely covered in ice, and this process may have begun around 2.4 billion years ago. During this time, changes in the composition of the atmosphere, linked to a sharp increase in the concentration of carbon dioxide and methane, could have led to global cooling. Scientists believe that as a result of these changes, the temperature on Earth dropped to a critical level, turning the oceans into icy deserts and covering the planet's surface with an ice sheet several kilometers thick in some regions. Imagine a world where only volcanic islands, sticking out of the icy ocean, become rare oases of open water. In such conditions, life would be almost impossible, and only the most resilient organisms could survive in the vast expanses of ice. This harsh climate acted as an evolutionary filter, selecting the most adapted forms of life. For example, in such conditions, only microorganisms with unique metabolic capabilities, allowing them to use limited resources, could have survived. According to researchers like David Butte, who actively studies this hypothesis, it was during this time that primitive forms of life, adapted to extreme conditions, could have emerged. There is evidence that some of them, such as archaea, could have developed in hot springs, where the water temperature remained above zero, creating unique ecosystems that could have existed under a complete ice cover. Scientific data shows that such organisms could have used chemosynthesis to obtain energy, making them independent of sunlight. This hypothesis emphasizes how harsh conditions could not only destroy many forms of life, but also lead to the emergence of new, more resilient organisms capable of surviving in the most extreme conditions. Research conducted in the last decades shows that such events could have repeated over millions of years, indicating the cyclical nature of climate changes that had a profound impact on the development of life on Earth. During such ice ages, the biosphere was subjected to significant stress, and only the most adapted species could continue to exist, ultimately leading to the diversity of life forms we observe today. Studying these processes is important for understanding how life on Earth could adapt to extreme conditions and how modern climate changes can affect the ecological balance. As a result, some of these early forms of life could have become the ancestors of modern organisms, which has enormous significance for the study of evolution. Eukaryotic cells first appeared approximately 2 billion years ago and marked a true revolution in the biological world. Unlike prokaryotes, which were simple and straightforward, eukaryotes are more complex organisms with a nucleus and organelles, functioning like miniature cities with a clear organization. Inside these cells, life begins. The nucleus manages processes, much like a city hall, while organelles, such as mitochondria and the endoplasmic reticulum, perform their functions like various services and enterprises. While prokaryotes like bacteria mostly existed as solitary organisms, eukaryotes opened the door to multicellularity, laying the foundation for the emergence of complex organisms, including plants, fungi, and animals. This evolutionary process demonstrated how cellular organization can develop, enabling the creation of more complex and specialized functions. As a result, eukaryotes were able to adapt to various environmental conditions, contributing to their spread and diversity. Scientists such as James Watson and Francis Crick emphasized the importance of cellular structure in their DNA research, showing how genetic information is organized and transmitted in more complex organisms. This step in evolution was not just a change, but a true turning point that laid the foundations for the formation of ecosystems where different species could coexist, interact, and develop. This transition from simple cells to complex structures opened new horizons for biology and became the basis for the emergence of multicellular organisms, whose diversity we observe today. Eukaryotes became key players in ecosystems, occupying various niches and adapting to constantly changing conditions. An example of this is how algae, being eukaryotes, began to release oxygen into the atmosphere, leading to what is known as the oxygen catastrophe around 2.5 billion years ago, when the oxygen level began to rise sharply, significantly impacting life on Earth. The theory of endosymbiosis, proposed by the Russian biologist and evolutionist Aliluev in the early 20th century, is based on the assumption that some organelles of eukaryotic cells, such as mitochondria and chloroplasts, originated from bacteria that were engulfed by the ancestors of eukaryotes but not digested. This process, known as endosymbiosis, is a unique example of biological cooperation at the cellular level. For instance, one cell, possibly a primitive prokaryotic bacterium, could have captured another, providing it with protection and access to nutrients. In return, the captured bacterium provided its new host with additional energy resources through processes such as cellular respiration or photosynthesis. This interaction, which likely began around 1.5 billion years ago, gave rise to the formation of complex multicellular organisms. Moreover, such unions could have occurred not once or twice. Throughout evolution, there were numerous instances where cells engulfed others, forming new, more complex cellular structures. For example, mitochondria, which we find in every eukaryotic cell, are descendants of proteobacteria capable of aerobic respiration. Chloroplasts, responsible for photosynthesis in plants, originated from cyanobacteria that established symbiotic relationships with plant cells. These examples highlight how competition among single-celled microorganisms could have laid the foundation for complex life structures. Furthermore, research conducted by scientists like Kenneth Carlson and his colleagues in 2005 showed that such symbiotic relationships could arise in various ecosystems, indicating the universality of endosymbiosis as an evolutionary mechanism. Interestingly, Similar processes are observed in modern ecosystems, where organisms exchange resources, creating symbiotic relationships that promote the survival of both partners. Over time, such evolutionary changes have led to the formation not only of complex cellular structures, but also to the emergence of the biodiversity of living organisms that we observe today. The first multicellular organisms appeared around 800 million years ago and represented a significant step in the evolution of life on Earth. They were primitive colonies of cells that began to unite to increase their chances of survival. These organisms were likely similar to modern siphonophores, which are colonies of cells, each performing a specialized function. Unlike plants and animals, they inhabited a world of dark depths in the ancient seas. Each cell in these colonies could perform a specific task, such as one cell responsible for movement and another for nutrition, allowing the organisms to more efficiently utilize the resources of their environment. These colonies could reach sizes of several centimeters, which was a remarkable achievement for the time. These simple multicellular organisms, although primitive compared to the forms of life we observe today, laid the foundation for the subsequent evolution of more complex life forms. Their existence was a revolutionary step, as they initiated the process of cell specialization, leading to the formation of tissues and organs in later organisms. For example, a study conducted in 2012 by scientists from the University of Cambridge showed that such colonies could effectively use photosynthesis thanks to some cells containing chloroplasts, allowing them to survive in low oxygen conditions. These early multicellular beings were important players in the ecosystems of their time, creating complex interactions with other organisms, such as single-celled algae and bacteria. This interaction contributed to the development of more complex ecosystems that continued to evolve over the following millions of years, paving the way for the appearance of the first animals. By the time more complex organisms, such as trilobites and starfish, emerged on Earth, multicellular organisms had already become an important part of the marine flora and fauna, and their legacy continues to this day. 800 million years ago, life began its transformation, opening the door to the incredible diversity of life forms we know today. The Ediacaran biota, which existed approximately 600 to 500 million years ago, is considered the first known multicellular life on Earth. These organisms, unlike anything we know today, had a flat and soft-bodied structure, making them entirely alien to our modern understanding of life. Imagine a seafloor covered with strange creatures resembling leaves or feathers, gently swaying in the soft ocean currents. One of the most famous representatives of this biota is Dickinsonia, an organism that could reach up to 1 meter in length. Its form resembled a symmetrical covering made up of segments resembling leaf veins. These organisms lacked a hard skeleton and were not predators, creating unique conditions for their existence. In this world without predators or intense competition, the Ediacaran biota thrived, filling the oceanic expanses. Research shows that they could absorb nutrients from the water using their soft surfaces. Findings from places like Australia and Laurentia give us an idea of what these organisms looked like. In particular, fossils discovered in the Ediacaran Hill in Australia have allowed scientists to understand how these creatures interacted with their environment. The Ediacaran biota also challenges traditional views of evolution, as their existence preceded the appearance of hard skeletons and predatory species. This raises a mystery for paleontologists. How did these organisms evolve into more complex forms of life known to us later? It is important to note that they left very few fossils, which complicates the study of their biology and ecology. The lack of hard body parts means that many of them simply did not survive. The process of fossilization, which usually requires hard structures for preservation, could not capture their strange forms. Research has shown that the Ediacaran biota likely existed in oxygen-rich oceans, allowing them to develop in conditions we cannot imagine today. Paleontologists like Dave Pegg and Matthew Lake continue to study these fossils, trying to establish a connection between the Ediacaran biota and later forms of life. These studies help us better understand how life on Earth could have evolved in conditions completely different from today's. The Ediacaran biota is not just a part of Earth's history, it is the key to understanding the first steps of life on the planet. In this context, the study of Ediacaran organisms allows us to look back in time and see how life could adapt and change in conditions that seem incredible today. Studying the history of our planet, it is impossible not to ponder its incredible journey from a molten sphere to the cradle of life. Imagine Earth as it was forming. Fiery volcanoes spewed lava, and the atmosphere was composed of toxic gases like methane and ammonia. This poisonous cocktail seemed to leave no chance for life. However, over millions of years, due to cooling and interaction with water, oceans formed on the surface. These primeval bodies of water became the place where life began. The appearance of simple single-celled organisms, such as archaea and bacteria, marked the beginning of a long and complex evolutionary path. Over billions of years, the planet endured numerous cataclysms, from rapid warming to ice ages that reshaped landscapes and climate. These changes not only formed continents, but also contributed to the diversity of life. The uniqueness of our world lies in the fact that it became home to an infinite variety of living beings, from microscopic algae to giant dinosaurs. Each of these stages is a result of an endless process of adaptation and survival. We can only marvel at how life, capable of beginning in such harsh conditions, managed to survive and develop. Remembering this, we should note that lying in bed, we can study the history of our planet, exploring its mysteries and riddles, as if traveling through time. Our ability to appreciate this incredible legacy gives value to every moment. At the end of this night journey into the depths of time, do not forget the ancient seas where the first sparks of life ignited on young Earth. Good night and deep, peaceful dreams about the first migrations of organisms that became the foundation for all life on our planet.